Hello everyone, I want to welcome you to this last session on the second day of our user meeting. First of all, I have to disappoint you, so this talk will only be given by me, although in the program it says that Christoph will join me for this talk, but still all the slides and the whole presentation is based on several material of Christoph and me, so the spirit of Christoph will always be here in the talk. Secondly, I want to say, so what's the idea of this presentation? So first of all, I will talk, when this is working, I will talk, oh no, now, hopefully. I will switch, exactly. I will talk about the benefits of divergence conforming methods, whatever you choose, for incompressible flows. So for those who are familiar with the topic, incompressible flows or the discretizations of incompressible flows, there will be some things, and I want to convince you to use an HDF conforming method. For those who are not such experts in this field, but who are still interested in this topic, I also want to use this presentation as a short advertisement for this workshop I have tomorrow. So, and last but not least, for those who this talk is a little, for those who is this talk a little bit too technical, I have implemented a small game for you. So on my slides there will be some hidden small NGSolve logos. And if you will be able to find these logos, then you will at least know what we are going to talk about tomorrow. So if you are super excited about these topics, then I want to welcome you to this workshop tomorrow. Okay, so first of all, yes, this is a joint work with Christoph, who is with me in this talk, and of course also a joint work with Jay and with Joachim. Okay, yeah, who are from these institutes I don't want to talk about today. So we are going to talk about the discretization of the Navier-Stokes equation. So the first line, we have the velocity u and we have the pressure p and an external force F. And we have the first line, which is the conservation of momentum, and the second line, which is the conservation of mass. And we have some initial boundary conditions, and boundary conditions. And when we talk about the finite element discretization, we can talk about the generic FEM formulation for the Navier-Stokes equation, will look somehow like this. So we have a discrete velocity space VH, and we have a discrete discrete pressure space QH. And here we are going to talk about methods of lines. So we'll somehow apply discretization in the spatial domain in omega. So we still have here the time derivative, and then we have this discrete operators AH, CH, BH. So the AH will somehow be the discretization of the diffusive part. This CH will be the nonlinear convection term. So this is the important and tricky part for the Navier-Stokes equations. We have this B bilinear form, which corresponds to the divergence constraint, and we have this right-hand side. Okay, and we want to do some kind of a robust method, and so the question is, what are our robustness demands? And the first thing what appears is, when we talk about the Navier-Stokes equation, the first thing we will talk about is the Stokes equation. So you remove this time derivative, you remove this tricky nonlinear convective term, and you end up with this saddle point structure here. And for those who are familiar with the analysis of mixed methods, they immediately see what's going on here. So in order to have a robust method, you're not allowed to choose this VH and QH, so this discrete spaces arbitrarily, but you somehow have to choose them such that you have this LBB condition fulfilled, which corresponds to the divergence constraint. So this is the surjectivity of the divergence operator between the velocity space and the pressure space. And you need some properties so you need continuity and coercivity of the A bilinear form. And so the first thing here somehow tells you that you can at least solve the problem. And then when you apply the theory of mixed systems, you will get this kind of error estimate. And when you look at this, you will see, so of course you can bound the velocity error and the pressure error, but in particular we only look at the velocity error for now. And what tells you the analysis is that you can bound the velocity error by this right-hand side so some function on U. So here we have the hk plus 1 norm, but in particular also this p norm here. And I've already put this good question mark here. So the question is, should the exact velocity also depend on p, on the exact solution p? So this term then goes to pressure robustness. So the question if this is good or not good is somehow defined in a term called pressure robustness. I will come back to this later. Okay, so this is the first thing. We want to handle the Stokes equations. The second thing is, now we go back to the Navier-Stokes equations, you want to handle high Reynolds number flows. In particular, the difficult part here is that you should be able to handle the convection, so you should be able to handle this non-linearity. So for example, you have this two-dimensional Kelvin-Helmholtz instability problem here. And the big question is, what does this mean, high Reynolds number? So for those who are familiar with this, you immediately know what's the problem here. But to give you somehow a feeling, what's the difference between a high Reynolds number flow and a low Reynolds number flow, we will look in particular at this Kelvin-Helmholtz instability. So what's the setting? We have the unit square, so it's a two-dimensional flow. We have periodic boundary conditions on the right and on the left. And we have this initial velocity going to the right at the top and to the left at the bottom. And we have a small perturbation here. So here we have a nice video, what's going to happen. So here we have 3 times the same initial condition at the beginning, and here we have the Reynolds number 100, here we have the Reynolds number 1000 and 10,000. And depending on the Reynolds number, you see that the bigger the Reynolds number gets, and there appear to be much finer structures. So in particular, when you have this convection term, this nonlinear convection term, you somehow have to be able to deal with this fine structures here. So you see here you have much smoother velocities, everything is smoothened out, so this corresponds to a lot of diffusion. So if you have a small Reynolds number, this is not really a problem, so the big question is what's going to happen when you have this high Reynolds number flow. Okay, so this is a 2D example, and of course you can also do this in 3 dimensions. So here is, for example, the Taylor-Green vortex. So the big question is, what can you do to discretize such problems? And what, at least for our part, what we figured out is that the thing you want to have is that your velocity space is HDF conforming. And in particular, you want that the divergence of the velocity space is a subspace of the pressure space. So this is the choice we want to make. And now I will try to convince you why this is a good choice. Okay, so what are the benefits for such kind of discretizations? The first thing what we immediately see is that we have a local mass conservation. Remember, when we had this divergence constraint, this somehow tells you that when you have a fluid and you have a fluid water ball, for example, you can't press it together. You won't lose mass. That's what it means. And if you have such, if you have this property that the divergence of VH is the subspace of QH, then you will always get pointwise divergence-free velocity fields. Meaning that, remember, we are actually doing a finite element method, so we discretized all this somehow in a weak sense. So actually what you get with a normal or with a standard finite element method, you will only get that the divergence tested with a pressure function and integrated over the domain omega will be 0 for all these test functions in the pressure space. But if the divergence of VH is a subspace of QH, you can take one particular choice. You can choose QH to be the divergence of UH. And now when you plug this in, you will see that the integral of the divergence UH squared should be 0, and this will then, of course, tell you that the divergence of UH has to be 0 pointwise, so because this is a polynomial then. Okay, so just to give you a picture what is going on, what's happening here. So we have an HDF conforming method, so this applies to this picture here. We have a discontinuity in the tangential velocity, but we have a normal continuous velocity. So we have a continuity in the normal direction, so this is this green arrow here. So easily spoken, because this is normal continuous, everything what would go, for example, in this edge, and then inside the element from this edge will go outside from the other edge. This is just a mental picture here. Okay, what's the second benefit? This is the term called pressure robustness, so we already saw this, and this goes back to the following idea. So again, we are back in the Stokes setting, and we have an arbitrary right-hand side F. And the big idea, or the idea now is that if you have an arbitrary right-hand side F, what you can do is you can apply a Helmholtz decomposition. So you can somehow split this into a divergence-free function G and a rotational-free function gradient phi. So if you put this to the right-hand side, what you then realize is that, remember, our velocity actually, so the solution of the Stokes equation is a divergence-free function, so we can also test this with the divergence-free subspace of VH to see what are the terms actually seen by the velocity. And then when we plug this in, if we test this equation only with divergence-free functions, then what we see is, of course, this term will be 0, because the divergence of VH is 0, so this will cancel out. And if you apply integration by parts here, this term will also be 0. So what we see here is that the velocity UH, and also the velocity UH, is only steered by the divergence-free part of the Helmholtz decomposition of the right-hand side F. So, easily spoken, this holds true for the exact solution U. So U is only a function F of U, because the exact solution U depends on G. But the important thing here is that also if we have this property, if we have this pressure robust method, that the discrete velocity is also only a function of U. So you don't have this pressure dependency anymore. And the final thing is that we have energy stability. For this, again, a mental picture. So think of a glass of water, and now you are the right-hand side F, so you are the force, and you steer around in your water, and you have this movement, and suddenly you stop, you pull out your finger, and you have this movement of your velocity, and the big question is what is happening now? And because we have this fluid and we have this fluid particles, there will be some kind of a diffusion. So when time passes on, so if we wait some seconds or some minutes, at some point there should not be a movement anymore. And if we translate this to the mathematical setting, then the big question is, what's the time derivative of our kinetic energy? So what's the time derivative of the inner product of UH and UH? And you can see this, for example, if you pick the right-hand side F equals 0, and you do a symmetric testing of your formulation, and put everything on the right-hand side, then you can get this equation. And we know already, so this AH corresponds to the diffusive part, so we know that this is the proper sign. This is greater equals 0. So here, when we have a minus, we see that the time derivative is negative, so it will decay in time. The big question is, what is with this convective term? And the thing is, when you use an appropriate stabilization, for example, this upwinding stabilization, and then you can show that this nonlinear convection term is also greater equals 0. And the crucial part here is that your discrete velocity is exactly divergence-free and normal continuous, of course. Okay, so of course we have not invented this HDF conformity, so there were a lot of people who have done this, and here is at least I tried to do a short overview. So you can also do this in the H1 setting. This was done, maybe people know the Scott-Vogelius element. This is in 1985. The problem here was that you need some kind of a special mesh, so you need a barycentric refinement here. And then there are different ways to achieve HDF conformity. For example, you can do this by HDF conforming DG spaces. So for example, you use a BDM space or a Ravier-Thomas space, and you abandon this H1 conformity and implement it with so you have a weak H1 conformity only. You can also do this when you use if you just use a DG finite element space with constraints. So you use your standard DG spaces, so for each component, and you enforce this normal continuity through Lagrangian multipliers, and this is in fact quite equivalent to this HDF conforming setting. So, for example, Rehbergen, who is here in the audience, where is he, is doing such things. What is also interesting is what people are doing is that they use standard DG methods, and they only enforce normal continuity and the divergence-free property through penalties. So they do not have it in a pointwise exact, so they are not pointwise exact divergence-free, but they only converge to this HDF conforming solutions. For example, people from Munich, so Kronbichler, Valfen are doing this. And finally, I want to mention this last thing here. So this is a quite new thing. We realized that you can actually rewrite the Stokes system in a mixed way, and we will see just in a moment how to do this. And then we actually realized that this HDF conformity, which was somehow non-conforming in this standard Stokes setting, is suddenly conforming. So what we more or less focused was, so Joachim and Christoph, was this setting, or to be precise, in a hybrid setting of this version. And what we realized, so me and Joachim and Chase, was this method here. I want to mention that there was also a HDG method, which was quite similar or close to our method by Coburn and Sayers. Okay, so what is this method what we are going to talk about? So consider the standard Stokes equation. So this is the standard Stokes equation. We have this pressure and we have this diffusive part here. And what you do when you want to do a mixed formulation, think of the mixed formulation of the Poisson equation. You introduce a new variable sigma, and you say that sigma should be equivalent to the gradient of u. So you have a new variable sigma here, and you have this new equation. And when you do then the analysis, it turns out that there are different options for the choices of the velocity space and the sigma space. So if you just think of this first equation and you want to derive a weak formulation, then you multiply this with a test function and integrate over the domain. And then there are different options. The first option is sigma is in L2 and u is in H1, or you do apply integration by parts. Then you see that sigma should be row-wise in HDiff and u should be in L2. But remember, our goal was that the velocity space is given by the HDiff space. And then it turns out that if you do the analysis, you can look at my PhD thesis, for example. If you do the analysis, it turns out that the proper space can be chosen in the following way. You choose the velocity space as the HDiff, the pressure space, so nothing changes here, so you have this L2 space. And the sigma space is this H curl diff space. I don't want to go too much into the details here. We will talk a little bit tomorrow in the workshop about this. But just at the end, so don't be scared. However, you can already rewrite the Stokes equation in the continuous setting differently by applying this, by choosing these functions. The big question is, of course, how can we discretize this system? And this is what we call the MCS method. And here we can now choose the following spaces. So we choose this HDiff conforming Ravier-Thomas space, for example, the appropriate pressure space, pk. And the big question is, how can we discretize this fancy H-curl diff space? And this is now quite similar, or goes into the direction as the space Joachim already told us yesterday he uses for elasticity, because there he had the H-diff space, and now we have the H-curl diff space. And in fact, it turns out that the proper discretization can be done choosing tensor-valued polynomials of order k. I just realized I used two different symbols for the polynomial space, but you use polynomials of order k, tensor-valued, which are normal tangential continuous at edges. So you are at the edge in 2 dimensions, you multiply it with the normal vector from the right-hand side and the tangential vector from the left-hand side, and this quantity is continuous across these edges. Okay, and then this is more or less exactly the same system as we had on the slide before. You only have to change this in duality pair here in a discrete setting, but more or less this just is the divergence of sigma. Oh no, this should be a tau. This should be a tau h, sorry. But this is more or less just a divergence on each element plus some terms which appear because we are not exactly HDiff conforming in each row. You may now ask, okay, yeah, this sounds great, but you have now introduced a new variable sigma and a lot of degrees of freedoms, and the matrix gets super big. What we do, in fact, for example, in the model templates where we use 3 minutes. You said I have 30 minutes. No, you said I can still have 30 minutes. Okay. Yeah, you can hybridize this and compress this space. In NGSolve, you can do this by this compress function. Okay. Really? I only have 3 more minutes? Okay. Now I wanted to talk about the implementation of the Navier-Stokes equation, and this more or less goes back to the ideas Christoph told us yesterday already. So you use this IMAX type schemes where you do a proper splitting into an implicit method and an explicit. So we somehow efficiently do an efficient operator application of the convection term, and we do an efficient solution of the Stokes-like linear system where we have the divergence constraint and the diffusive part. We also talk about this tomorrow. For the convection, I already mentioned this, we wanted to have energy stability, so we want to have this greater equals 0, and the crucial part is that you have this exactly divergence-free velocity fields, and we do here an upwind stabilization to get this property. Of course, we also need to solve the initial Stokes problem, and this is something new. So for big problems, we need some kind of an iterative method. So remember, we have a saddle point structure. We are not allowed to use a CG method. So what we are doing is we use a Prandtl-Bastiak transformation. So we apply certain transformations which lead to a SPT matrix again, which allows us then to use a CG method. And then to solve this system, we need the inverse of the stiffness matrix A and the pressure Schur complement S. And for very big systems, of course, we need a precondition CG, and there we use this auxiliary precondition. I don't want to go too much into detail now, but this is something Joachim already mentioned today. Some further benefits I have to skip now because I don't have any more time, but we have a pressure-robust LBB constant, and we are Reynolds RE semi-robust. You can ask Christoph about this. We can do 2D examples, we can do benchmarks, we can do 3D examples, and this is what we are going to talk about tomorrow.